And the basic idea with induction is we're going to do the first step, and then we're going to show that the nth step will imply the n plus 1th step. So the basic idea is we'll start by proving P of 1, which is some statement involving 1, and this is called the base case. And then we'll do some other statement, P of n, and this is normally going to be related to the statement that was given to us, and we're going to try to show that P of n implies P of n plus 1. And this is what we'll call our inductive step. So you should have already seen a lecture on this. This was, I think, the last thing I lectured on before the whole coronavirus thing took over. So I'm going to be reviewing that, and this is, again, this is called mathematical induction. You probably want to know that. So let's start with an easy example, and I don't say easy because it's easy, but just easy relative to the other examples that we'll be doing. And so the first example is show that the sum as j goes from 1 to n of j is equal to n times n plus 1 over 2. So this one we already did in class, but let's do it quickly. So first, I want to mention somewhere in my proof that I'm doing this, by way of induction. So by induction, something like that. And then I'll start with my base case. Now the base case, I guess I should, so for all n natural, should give you a proper statement, I guess. So for the base case, I'm typically going to start with the smallest example of my statement. So the smallest is going to be what if n is equal to 1. That's not always the case, but for our class, that's a pretty safe assumption. So then what I want to show is this is true for n equals 1. So I check, what does this mean when n equals 1? So the base case, remember, I'm trying to show my statement, my P of n, for n equals 1. So P of n is sum j goes from 1 to n equals n times n plus 1 over 2. And here I'm doing the case that n is 1. So we set n equal to 1, and we just plug in and see what happens. So if n is equal to 1, I have the sum as j goes from 1 up to, well, n is 1 of j. And what's that going to equal? Well, that's just 1. And on the right-hand side here, I've got 1 times 1 plus 1 over 2. And this is 1 times 2 over 2. This is 2 divided by 2, which is, again, 1. So we've just shown our base case. We're happy with that. Little reminder, this is natural numbers. Natural numbers I've defined as the set 1, 2, 3, ... So not including 0. Anything else? Oh yeah, so this summation notation, the sum as j goes from, let's say, 3 up to 7 of, let's say, 2j, just a quick example reminder, is going to be, 2 times 3 plus 2 times 4 plus 2 times 5 plus 2 times 6 plus 2 times 7. We just plug in j here for every value between 3 and 7 inclusive. That's how the summation notation works, if you're a little rusty on that. Okay, so let's move forward. We've done the base case, and now I want to do this inductive step. So I've shown that this is true when n equals 1. Now I want to show that if this statement here is true for n, that it's also true for n plus 1. So that's what I'm going to call the inductive step. And I'm going to say, well, let's assume that this is true for n. So I'm going to assume this is true for n. That is that j, the sum as j going from 1 to n of j, is equal to n times n plus 1 over 2. Let's assume that, and we'll try to imply that this statement is true for n plus 1. So it might be helpful, again, this is sort of my scratch work column over here. I do have a dog in the background playing with a toy, so if you hear the errant noise, that's what that is. And he's super cute. If you can get through the whole lesson, I'll show you some video of the dog. Okay, so what we want to do is we want to imagine what is the version of this statement when n equals, or sorry, for n plus 1. So we've got it here for n. Now what is this statement for n plus 1? So I like to call this my goal cloud. So this is where I'm writing my goals. So I'm going to write down the exact same thing that I wrote down here, j equals 1, except wherever I see an n, I'm going to put an n plus 1. So this is my goal for my left-hand side. My right-hand side, the goal is going to be, well, that n should be an n plus 1. This n should be an n plus 1. So I'll get n plus 1, also known as n plus 2. And then 2 is still a 2. Since this is a goal, I like to pretend that it's in a thought bubble. And because a thought bubble kind of looks like a cloud, I like to call it my goal cloud. And that kind of sounds like glow cloud from Night Vale, so I call it my goal cloud. All hail. And the basic idea is this is P of n, this is P of n plus 1. Okay? This is what I'm assuming in my inductive step, and I want to derive this from this. That's going back up here. This is, I'm starting with this, I'm trying to derive that. So I want to start here and somehow get here without just changing variables. So one mistake a lot of people make is they write this, then they write that, and then they think they're done. But that's not quite the case. So you want to start here, you have a goal in mind, but you need to get from here to there without just changing the symbols. So we need to use math skills to get from here to here. So let's try manipulating this until it gives us this. Now there are a number of heuristic reasons to choose one or the other way to manipulate, but what I tend to go with is whatever I learned most recently. So I learned about addition and multiplication and division and parentheses in, I don't know, elementary school or something, but I didn't learn about summation notation until high school. So this side is more recent to me. Again, this is not always going to work, but this is just a heuristic. So I'm probably going to mess with this side. So I want to look at what are the characteristics of the left-hand side that I need to change to get the left-hand side over here. So here I've got the sum of n numbers. Here I have the sum of n plus 1 numbers. Okay, so what this means is 1 plus 2 plus 3 plus ... plus n minus 1 plus n. That's what this left-hand side means. But what this left-hand side means is 1 plus 2 plus 3 plus ... plus n plus 1. So this one is a lot like this one, except it has one more term in the sum. So to make this thing become this thing, I just need to add n plus 1 to both sides. Okay, so this is just sort of scratch work here. So now I'm going to add n plus 1 to both sides. So I've got the sum as j goes from 1 up to n of j. Now I'm going to add n plus 1. Now on my right-hand side, I've got n times n plus 1 over 2. And since this is an equation, I can't just do something to one side and not the other. So I've got to add that same thing to both sides. And here's where a lot of people tend to get lost. So a lot of students that I've noticed over the years will add n plus 1 to both sides and then just kind of say, I don't know what to do next. And that's okay, you know, do the best you can. But what I'd really like to see is now that I've set up this left-hand side the way I want to, it should be the sum as j goes from 1 to n plus 1 of j. And the right-hand side, well, I need to think about how to make that into this. Well, since I'm adding fractions, I'm going to give them a common denominator by multiplying and dividing by the same number. Now, I've got how many n plus 1s upstairs? So I've got something over 2. And the question is, how many n plus 1s do I have? Well, I've got n plus 1s, and then I've got 2 more n plus 1s, for a total of, how many n plus 1s do I have? N plus 2 of them. And we notice this is precisely what was in my goal, and therefore I'm done by induction. So I can draw my box, I can color it in. This is sufficient for me. Okay, so you have questions, email me. Since you made it to the end, let me go try to find my dog. Here he is. Where's my puppy? Oh, you cutie. Oh, you cutie. All right, thanks and good luck, everybody. All right, so hopefully you've got some understanding with the first induction question that we've gone through, the first induction example we've gone through. So now let's do another one. Yay, more induction. So I want to go through just some more complicated induction problems to make sure that we can really do this. So here's an example. Use induction to show that for all n natural, we have the sum, as j goes from 1 up to n, of j squared is equal to n times n plus 1 times 2n plus 1 over 6. So we're hoping now to follow kind of the pattern from the previous example and prove this is true for all natural n. So we'll start as before. We'll say by induction, and we'll start with the base case. The base case is going to be the case when n equals 1, right? We call this the P of 1 case. Now, 1 might not always every single time be the base case, but for examples with the natural number, with natural numbers, it's a pretty safe bet most of the time. In our class, I probably won't be doing a whole lot of complicated stuff using other types of induction, but it's just worth knowing that that's not always the starting point. Anyways, let's show that that works here. With trying to prove this for n equals 1, we're going to end up with the sum as j goes from 1 up to 1 of j squared, and that's just 1 squared, which is of course equal to 1. One big 1. Now let's look at the right-hand side. I've got 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6. Well, this is just 1 times 2 times 3 over 6, which is of course 6 over 6, which is of course 1. So we're happy. What we've done is we've shown that this equality holds for n equals 1. And this whole equation here I'm calling P of n. This is some statement involving n. So we've shown that this is true when n equals 1. Now let's do our inductive step. And remember, the inductive step is we want to show that P of n implies P of n plus 1. So what we typically do is we start by writing out P of n. So here's P of n. The sum as j goes from 1 up to n of j squared is equal to, actually let me leave a little bit of space, is equal to n times n plus 1 times 2n plus 1 over 6. And then we want to get, so this is my P of n, again I just rewrote this thing, we want to get to P of n plus 1. So P of n plus 1 now, I'm going to just write this off to the side. This is kind of my goal. This is what I want to get to, and it's going to be just P of n, so the sum as j goes from 1 up to n, except replacing n by n plus 1. n plus 1 of j squared equals, now here, I'm going to replace each of these n's by n plus 1. So I've got n plus 1 times, this n plus 1 becomes n plus 2. And now 2n plus 1 is going to become 2n plus 3, all over 6. And why did that become 2n plus 3? Because when this n is replaced by an n plus 1, I've got 2 times the quantity n plus 1. So that's 2n plus 2 and then plus another 1. Again, that's when I replace this n right here by n plus 1. Okay, so now what we did in the previous example was we looked at this thing and we tried to make it look like this thing. Oh, this is my goal cloud. I'm going to put it in a cloud. This is my goal cloud, all hail. Never miss an opportunity for a Night Vale reference. And then I need to somehow do math to make this equation imply this equation. Okay, so fundamentally what I'm doing is I'm assuming that this is true, and I want to use this to imply that this is true. So not just changing variables. It's not true by change of variables. That's not how this works. I've got this, then I kind of did a change of variables to get this to be n plus 1 and get all these, but that's just showing me my target. That's just showing me my end goal. Now, how do I mathematically manipulate this to get that? Well, this is the sum of n terms. This is the sum of n plus 1 terms. So kind of like the previous example, I'm going to add the n plus first term in. Now, there's a danger. That doesn't just mean we add n plus 1, because here we're summing up squared numbers. So I'm going to add n plus 1 quantities squared. And if this is mysterious, let's write out what this means. Well, this is 1 squared plus 2 squared plus 3 squared plus ... plus n squared. So how do we get this thing to be the sum of n plus 1 squareds? Well, the next step in the pattern is going to be n plus 1 quantity squared. This is just sort of scratch work. That's what's going on here. Okay, but I can't just add n plus 1 squared to the left-hand side. I've also got to add it to the right-hand side. N plus 1 quantity squared. And then over here I'm adding fractions, and we know how to add fractions. We get a common denominator, so I make sure that I can't just divide this by 6, I also have to multiply it by 6. And now let's try to get this right-hand side to look like that. So this left-hand side should work out, and why do I think that? Because it's the sum of the first n squares plus the n plus first square, so it's the sum of the first n plus 1 squares. So this left-hand side is precisely what I want. It is the sum, as j goes from 1 to n plus 1, of j squared. And the right-hand side is a bit of a pill. So let's do our best with that right-hand side. So I know I'm going to have something over 6. And what I want to do is I want to factor out n plus 1s. So let's see how many total n plus 1s do I have. Well, here I've got n times 2n plus 1 n plus 1s. And here I've got 6n plus 1s. Sorry. 6 times n plus 1 n plus 1s. Right, because this is n plus 1 quantities squared. So what's happening here is I've factored out one of those factors of n plus 1, and I've still got that other factor of n plus 1. If this seems like magic and you're not sure how this turned into this, I would recommend you try to multiply this out and multiply and add this all together and see that you get the same thing. Okay? Basically, I have how many n plus 1s here? Well, I've got n times 2n plus 1 n plus 1s from this fraction, n times 2n plus 1. How many n plus 1s do I have here? I have 6 n plus 1 n plus 1s. Because 6 times n plus 1 times n plus 1, this is again just the numerator, is 6 times n plus 1 times n plus 1. I have factored out a factor of n plus 1. All right, now there might be a clever way to do this. I don't know it. So what I'm going to do is, okay, I can come up with a quicker way, but I don't know a super clever way to show that this equals that without sort of pulling some tricks out of the hat. So let's just, without trying to predict the future, let's just simplify this expression in the square brackets and then show that we can factor it into that expression. Okay, I think that's just going to be a little bit simpler for us. So I'm going to keep the n plus 1 here. And I'm going to simplify this expression inside here. I've got 2n squared plus n plus 6n plus 6. And this is all over 6. And I notice now I have the left-hand side of my goal cloud, and I almost have the right-hand side of my goal cloud, except, you know, I've got this factor, and this part of the denominator is right, and the numerator I've got this factor, but then I've got this mess here instead of these two factors. So what I want to do is I want to just try multiplying these two factors together and see what I get. So let's FOIL, you know, n plus 2 times 2n plus 3. And by the way, I recommend having, you know, scratch work, having a place to just write down things that maybe you can do in your head, but maybe you'd have a little bit of trouble. So then I do 2n squared, that's first, then outer, n times 3 plus 3n, inner, 2 times 2n, 2 times 2 is 4n, and then last, plus 6. So 2 times 3 is 6. So this simplifies to 2n squared plus 7n plus 6. Hey, guess what? This also simplifies to that. So I have left-hand side is j goes from 1 to n plus 1 of j squared equals n plus 1 times, this is, we'll simplify this, this is 2n squared plus 7n plus 6 all over 6. And now I did the n plus 6n here. I know now that I can factor this into n plus 2 times 2n plus 3. Now some of you might have just looked at this trinomial and said, oh, I knew I could factor that, and that's really great. But just my experience has shown me that students that are taking this discrete mathematics class oftentimes are a little rusty on factoring. So I just want to give you some confidence and say, even if you don't remember exactly all the factoring tricks and all the little rules of polynomials, you can just check. So this is going to work out. N plus 1, I know I can factor this now into n plus 2, 2n plus 3, because I just checked that. If that seems like magic, notice that the only thing that changes over this equal sign here is the thing in the square brackets becomes this, and we just checked that the thing in the square brackets is equal to that. Okay? So now we are done by induction. We get to draw our little box and color it in.